Let's see here. Did I? Yeah, okay, we're good. I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for these students in this class and just ask you to help us to finish well this semester, Lord. And I pray, Lord Jesus. Amen. So I did post the solution to test 2 at long last. So it's in Canvas, and if you have any questions about that, obviously let me know. If you guys have any questions about like current anything? No? Yeah.
Is this one in Canvas already?
No, I have not. I did write it down on a piece of paper though, so I have those. But I have not implemented those yet because when I did it, I was still partly uncertain about the test 2 grades, and I'm adding those points to test 2, which means that I think you guys will probably keep your test 2 grade because I may have been a little bit too generous with the regrade. Anyway, be sure to tell Violet. But anyway, but yeah, I will take what I put on that paper and then add it to your test 2 once I hopefully today. I want to talk to you guys a little bit about what I would call metric geometry. It's kind of the final topic, I suppose, this semester. And so the question is, well, what is a metric geometry, right? A metric geometry is a vector space paired with a metric. And of course, that begs the question, well, then what's a metric, right? So I'm using the term metric more like a physicist at the moment. So I probably should be clear what I mean by that. So here's the definition. A geometry is a vector space, let's say V, paired with a metric. All right. So you might say G. So you could write VG is a geometry, right? You can think about them as a pair. Right. Now here, what I mean by a metric, we define a metric is as a symmetric I should probably start with bilinear. Bilinear, symmetric, non-degenerate. Form on V. And so what I mean by that, let me spell that out with some equations rather than just words, is, let's see here, that is, G is a mapping from V cross V. Golly, I'm a little bit torn. I think I have a problem in your homework, which the I think the inner product is over a complex vector space, so I probably need to put the field here. But I really want to keep it real, but I'm gonna put F there because I do think one of your homework problems has a complex inner product space. So like, so for the sake of the homework making sense, I'll put F there. But either of the reals or the complexes again, okay? And so number one, bilinear, of course, means that G of Cx plus Y Z is C times G of X comma Z plus G of, well, you guys know the drill. And also G of X comma CY plus Z, C times G of X Y plus, ooh, I'm going to put a real here because I think as soon as I write that it's bilinear, I'm pretty much ruling out the complex case, right? Because the complex case is not bilinear. The complex inner product is, like sesquilinear. And we would like inner product. We would like an inner product to be a special case of the more broad idea of a metric. Okay? So, yeah, I'll keep it real. My apologies to your homework problem, but you'll forgive me. Okay, so I may owe you an announcement to try to interpret the homework problem. I'll try to think about that for you guys. So it's bilinear. Number 2, it's symmetric. So that's g of xy is equal to g of yx, right? For all x and y in the vector space. Of course, this was for all x, y, and z in the vector space, and c in the reals, apparently. And what does non-degenerate mean? So what that means is if we have g of x comma y is equal to 0, all right, for all x in V, that implies what? That implies y is equal to 0, right? So this is what we mean by metric. The difference, so observation and inner product gives an example. Well, I don't want to say it that way. An inner product gives, listen to me. It's horrible. I need to throw out all these markers. Inner product is a metric, right? Is a metric. Inner product on V over the reals is a metric, right? So usually I would say something like this: V paired with a real inner product is an example of a Euclidean space. Although, honestly, when I talk about Euclidean space, I'm really usually thinking specifically about the example of Rn paired with the dot product. So, let me just make that a little bit more crisp definition. Rn paired with the dot product is the Euclidean geometry. All right, and I can make good on that terminology. You might be like, oh, that's not what we said in my modern geometry course. And that's right, we have certain rights and privileges in this course that are not present in that course, namely coordinates. So we can do things like, I don't know, give a formula for the angle between vectors like this, right? Like if x and y are not equal to 0, then the angle from x to y is defined to be the inverse cosine of x dot y divided by the length of x times the length of y, right? That's how we define Euclidean angle. And how do we define the length of a vector? Square root of x dot x, right? So we can define the length, right, of a vector. We can define angle between vector. We can define distance between points. right? What's the distance between 2 points? So basically, you have distance between points, you have the length of a vector, you have angle between vectors. You have everything you need to construct Euclidean geometry. Not a compass nor a straight edge in sight. Just beautiful, beautiful algebra. Right? You'd think someone, well, anyway, I should stop. I should stop. He's just teaching the course as it's constructed. It's not his fault. But anyway. Okay, so this is Euclidean. Now, what this is, but a metric is more general. Like an example. Example of metric which is not an inner product would be the following. We can define g of xy equal to like x transpose eta y, where eta is -1, 1, 1, 1, like that. And here on x and y in R4. So here R4 paired with this this metric is Minkowski space. This is the geometry of special relativity. Now, if I tried to do things like define angle between vectors or distance between points using this metric, I would be into a world of hurt. I don't want to get into it. It's complicated. There's not a triangle inequality. There's like this thing called the reverse triangle inequality. It's just a mess. If you try to go down the path that you've already are familiar with from Euclidean geometry in the context of a genuinely non-Euclidean geometry, it's very troublesome. And no, this is not that kind of non-Euclidean geometry from the other course. Well, anyway. So why is this not a metric? I mean, first of all, you know, little lemma. If we have, you know, if we have G, that's a mapping, say, from Rn cross Rn to R again, then there exists big G such that G of xy is equal to x transpose big gy, right? This is like what it means for it to be a bilinear form. In fact, we could talk about a bilinear form over an abstract vector space. I'm just trying to keep it concrete for our current discussion. But if I focus my attention just on the case of Rn, certainly we can write a bilinear form as a matrix multiplication, right? So if I just need one criteria here, bilinear, right? Then that, right? And then like number 2, if G symmetric, then what? What can you say about the matrix? Big G. It's a simple exercise. You can prove that G is also a symmetric matrix. So like symmetry of the bilinear form implies symmetry of the matrix, right? And now 3 is a little bit fussier. If G is non-degenerate, then it turns out that we can prove that G inverse exists. So do you guys remember what was our definition of inner product in the real case? It starts out the same, right? It's a bilinear form, right? and it's symmetric. I mean, we spent a lot of time in the possibly complex notation, right? So we had like that conjugation relation, right? And we assumed the sesquilinearity. Well, we assumed linearity in the first slot, right? And then we proved that we actually then had necessarily conjugate linearity in the second slot, right? But if you go back to that and you ask, okay, what does the definition of inner product look like just in the case of real vector space? That conjugate linearity in the second spot just becomes plain old linearity. So you have linearity in the first and second slots, bilinear, and that the axiom was the complex conjugation axiom, where we flipped the entries and we conjugated, right? Well, complex conjugation's nothing in the real case. It's just back where you start again, right? So that axiom just reduces to symmetry. So an inner product is necessarily bilinear and symmetric. But what was the third axiom in the inner product case? Do you guys remember? How do we write it? Well, I hope you guys better, excuse me. I hope you figure it out, because that's definitely something that might be on the final. Yowzers. Right? So, goodness gracious, I don't want to mess it up. I'm not sure if what I'm remembering off the top of my head is the definition or a derived result. So let me just double check for us. Make sure we're on the straight and narrow here. We mean the wrong pin. You shut up. There we go. All right. Do. Come on. All right. Come on. You know, I say inner product quite a few times in the notes, it turns out. Oh, it took me to the appendix. What is so very unhelpful. That appendix is just all AI nonsense anyway, you know that, right? Everything in my notes that seems out of character for me is AI, just for the record. All the errors, AI. Probably. I will eventually get to the start of chapter 5. All right, start of chapter 5. Inner product is a mapping on the Cartesian product of V with itself to the field, such that it's additive in the first slot. We pull constants out of the first slot. It's got that axiom 3 was the conjugation flips the order. And then if x is not equal to 0, then xx is an element of positive. So axiom 4 for the inner product was if x is not equal to 0, the inner product of x and x is an element of the positive reals. So this is true even in the case that we had a complex inner product. This was axiom 4 for inner product, right? Right, so it's positive if you're sure that x is not equal to 0, right? We can't have the inner product of a vector with itself to be 0 unless what? Unless it's the 0 vector. That's what that axiom says, right? That's important if we're going to make vector length based on the square root of the inner product with itself. Well, that would be really annoying, right? If we had the inner product of a vector with itself was 0, and yet the vector is not 0, right? That would make using the square root of the inner product with itself to define like the induced norm, that'd be very troublesome, right? So as we look at this Minkowski space example, notice that if we put x equal to like 1, 1, 0, 0, right? And if we calculate the inner product of that vector with itself, so we've got 1, 1, 0, 0 times minus 1, 1, 1, 1, right? This is the formula for the Minkowski metric, yeah? What do you get? Right, which is minus 1 plus 1, also known as 0, right? So this is not an inner product, right? It cannot be an inner product because it violates axiom 4. So x is known as a null vector of G. It's a non-zero vector x for which G of xx is equal to 0. All right. Now, it is also true that G inverse exists in the context of an inner product. Like my lemma is still true for a inner product. Like this lemma holds for the context of a metric, right? If we think about a metric on Rn, it's equivalent to saying that you've got a matrix, big G, that's symmetric and non-degenerate. Like every symmetric non-degenerate matrix, n by n matrix defines a particular geometry on Rn, all right? When you take G to be the identity matrix, it's Euclidean geometry. When you take G to be this eta on R4, it's called Minkowski space. And those are different geometries, all right? So, like, can you guys, how do you think we're going to prove 3? If G is non-degenerate, then G exists. Well, so like in a particular context of Rn, I have what? I've got, you know, oh man, where did I put it? So we have G of x comma y equal to 0 for all x, right? Let's write that down. So let's look at the proof of 3. So we have G of x comma y is equal to 0 for all, what was it, all for all x, wasn't it? This is what non-degeneracy, if we're assuming non-degeneracy, that's what we get, right? So what does that specifically tell us in terms of the matrix? It tells us that x transpose times the G of the matrix of the form, G, times y is equal to 0 for all x in Rn, right? So what can we do with that? I hope you guys can help me. This is something I get stuck on sometimes. Because it's not like, I mean, if I come to a problem that's a matrix column problem, I'm in my happy, you know, I'm in my happy spot, happy place. But this is I've got the variables in the row right? Like it's a row times a matrix is equal to 0 for all rows. Maybe, to make this something I'm more comfortable with, if we transpose this equation, maybe that will help us. What do you think? Let's try that. If I transpose this, what do I get? I get, x transpose g y transpose, which is, by the way, y transpose, g transpose, x transpose, transpose also known as x, is equal to 0 for all x in Rn, right? What do we want to show? To show G inverse exists, like what would you suggest we should do? What tools do we have at our disposal to try to prove that G is invertible? It's a square matrix, right? We don't really have a formula for it, except that it's defined in terms of the bilinear form here. I'm quite certain that it's because of axiom 3 that it's invertible. Because, for example, you could take the 0 transformation. It would easily satisfy axioms 1 and 2. It's symmetric, it's bilinear, right? But it's definitely not non-degenerate. Just send everything to 0. Any ideas? My intuition is that we can argue that the null space of G transpose has to be equal to 0. I think we can prove that. If we can prove that, we're good, right? Because then the rank nullity theorem says it has rank n, therefore it's invertible. Yeah? So notice that G transpose times 0, of course, is equal to 0. So therefore, 0 is a subset. This is the silly part, right? Oh man, this marker, this is the worst. This marker, oh my goodness, this marker. It's very, very bad. This one is the one that smells like death. Oh, it's so bad. I don't know why I don't throw that out. I really should just throw it out. All right. So on the other hand, suppose x is an element of the null space of G transpose, I guess, then, I'm sorry guys, I need to step back. Okay, 0 is definitely in there, that's fine. So I need to go the other way. X is an element of that. I need to show, I'd like to show that X has to be 0, right? Well, I just get G transpose X is equal to 0. I feel like this is probably contradiction that we need to go, right? Let's try contradiction here, yeah? Suppose X is not equal to 0. Then we have Oh, golly. I'm sorry, guys. I just have a mental block on this thing at the moment. I better move on. I'm sorry. I better stop spinning my wheels here because we already started late today. And ironically, this is actually a very good test question, which I would currently get wrong. I mean, there's really nothing particular. It doesn't have to be just for Rn, right? You see, this lemma equally well applies in the context we have G is just like a mapping from a vector space across a vector space, to the reals. And if we let, beta V1 through Vn basis for V, all right? Then, and we defined, Gij is equal to G of, say, Vi, Vj, right? So if you had this set up, then one, Gij exists. Well, golly, I'm going to write up here. So you can write Gxy equal to, G of some x upper I, v lower I, some y upper j, v lower j, right? And that's the sum of x upper I, y upper j, g vi vj, which is, excuse me, sum over I and j of like xi, g, I, j, yj, which of course we could write as x transpose times g times y, right? Like this kind of matrix presentation of the formula exists also for an abstract vector space if we're willing to work through a basis. And in that context, again, you could prove that that matrix would have to be symmetric and also non-degenerate. All right? So I'm sorry, I've got some kind of stupid mental block. It's not that hard either, guys. Like you could figure it out. You probably already know, and you're just not telling me because you enjoy my suffering and you're all bad people. But no, I'm just kidding. Anyway, I will fix it, but not at the moment. That said, you can see this is non-degenerate, right? Because the determinant of the Minkowski metric, the matrix of the Minkowski metric, is just -1. Right? So the significance of the null vector, in my example, these are light rays. When you do space-time, the vectors that have the same amount of, so like the meaning of the 0th component's time, and then these are space. And so this is the same amount of, the time and the space are equal. So this would be corresponding to like something going at the speed of light when you put this into physics terminology and so forth. And so the light rays are exactly the ones that are weird for the Minkowski metric. They're these null vectors. And in any event, there's that. All right, let me show you guys something, since I am having trouble formulating things decently today. So, if you have a metric, you can formulate an isomorphism between a vector space and its dual, all right, and vice versa. So let me try to explain that. This is the so-called musical morphism. So I have used the up-down index notation in here, right? We used like upper components for vectors and lower components for dual vectors, right? With the dual basis and all that. So let's see if I can express this. So if we're given, a vector space V over the reals, let's say, paired with a metric G, we can define an isomorphism of V dual and V as follows. All right. So suppose I want to do I'll call my isomorphism psi, and I guess I'll start with X, which is a vector in V, all right? Then I want to say that this is an element of the dual defined by, here as we go. So to define a dual vector, what do you have to do? How do you define a dual vector? I mean, it's a linear transformation, right? So if you say how it acts, then that defines it, right? It's a function. You wanted to say what happens when it takes in a value, so let's call the value y, right? So I need to define the corresponding dual vector to x, I need a linear transformation on V, right? So how do you take what's on the board and create an expression which is linear in both x and y? Why haven't and I've not done this before because today for the first time we're talking about geometry, right? I mean, we could have done it before. Actually, we did do it before in the process of building the adjoint map. That Reitz vector thing we did is this actually, but so just G of xy does nicely. That is linear in x and linear in y, right? And so basically this psi I'm defining is mapping from where to where. It's going from V to V dual, all right? And so the typical notation for this is it's the flat. The flat of x is equal to G of x comma whatever. Now, this is a dual vector, right? So we can ask what its components are, right? Let's try to figure that out. So, all right, so beta of x, not beta, this is the flat symbol. I just can't draw it worth anything, flat of x is equal to flat of x. I need a basis here, so the sum I equals 1 to n of this acting on what, v lower I times v upper I, right? That was our basis expansion. Remember, we had this before, yeah? And okay, but this is straight up the sum I equals 1 to n of g of x comma vi with v upper I. All right, but let's expand x into the basis as well. So we've got, the sum I equals 1 to n, g of the sum, let's say j equals 1 to n of x upper j, v lower j. Like that. And so I can use linearity of the metric, pull the sum out. I've got sum over I and j, ranging from 1 to n. And then I've got, g of vj, vi, and I'll write the xj over here because I can. I mean, you can write the xj whichever side you want. I mean, I guess I usually put it in front, but I don't know, whatever. Go either side. Okay, so the flat of x, the ith component of it is what? It's the sum, j equals 1 to n, of g, j, I, x, j. In physics, this is called lowering the index. So what they do is they say, oh, the flat of x, it's the same vector, just written covariantly rather than contravariantly. And so like physicists will just say this is equal to x sub I. See, what's going on here is you use the metric to lower the index. That's the that's the deal. So we can prove that this is, it's clearly linear, and you can easily prove that the kernel of this map is 0, right? Therefore, it's invertible. And the inverse to the map is usually called the inverse metric, which is a bit of a misnomer because, of course, like the metric is not invertible in the direct sense, right? Because it's like a mapping from the Cartesian product of the vector space in itself to the field, right? You can't invert that. But what you can do is find the inverse matrix. And so, like, definition, if you have big G is equal to Gij, then as a matrix, yeah, then G inverse, the notation that's used is this, G upper Ij. So this is so-called inverse matrix. And to complete this horrible story, the sharp, or is it the other way? I don't know. This is why I need Violet. Somebody who's a proper musician will tell me if I've written the sharp symbol wrong. Is it this way? Is it that way? Which is it? You can't trust me. I'm the person who does this rather than that. Correct me. Anyway, so the sharp, which is the inverse to this map, is actually the sharp is the inverse to the flat map in this language. And this sharp map will take you from, it allows you to convert a dual vector to a vector. All right. I will talk about this in further detail Wednesday. I think I've not talked about it enough for you guys yet. So what are we going to do Wednesday? Number one, I will fix that. So annoying. But in the remaining minute or two of class, I wanted to show you an actual calculation which should help you see how to do the homework. Right? That might be good. If I hadn't shut the thing, did I close it? Tell me I closed it. Oh man. Oh. Do you guys have any questions while I am suffering to find things? Rats. Well, that's no good. Well. All right, well, I'll put you guys out of your suffering. For now, I can't find the thing I wanted to show you, but... So I guess, I think you guys can do pretty much all the homework except for the musical morphism one.